Welcome to Study Loop.
This is the answer to Chapter 21, problem number 85 from the Smith Organic Chemistry textbook. This problem says an unknown compound D exhibits a strong absorption in its IR spectrum at 1692 wave number. The mass spectrum of D shows a molecular ion at M to Z 150 and a base peak at 121. The proton NMR spectrum of D is shown below. What is the structure of D? Okay, and so I'm going to actually approach this one a little differently than I've approached some other find the structure problems, because rather than, guess and check at a bunch of different molecular formulas to try to satisfy this M to Z of 150, we can use the NMR and the IR to get the pieces of this molecule. We can actually piece it together, and then we can use the mass spec as just kind of a check on what we've done. Okay, so the IR, the peak at 1692, that's definitely a carbonyl. So we know that we have a C double bond O in this molecule. We don't know whether it's an aldehyde or a ketone or anything like that. So then looking at the NMR, I'm going to jump around here too. So the last signal at 9.9 ppm, it's a singlet with an integration of 1. This is this is an aldehyde. So we definitely have an aldehyde in this molecule. The two signals above that are two doublets at 7 and 7.8 ppms. They each integrate to 2. So this is a para-disubstituted aromatic ring. Okay, so para-disubstituted aromatic ring. Our first signal is a 1.5 ppm triplet that integrates to 3. So this is a methyl group. It's split into a triplet, so it's next to a methylene group. And our second signal, the 4.1 ppm quartet that integrates to 2, is that methylene group. So we can tell that they're splitting each other because the methyl group is split to a triplet by the methylene group, and the methylene group is split to a quartet by the methyl group. And again, that's all from the N+1 rule. So we can actually put this molecule all the way together right now. So we have our aromatic ring, para-disubstituted. And so one of our sides is going to be substituted with an aldehyde. And our other side is going to be substituted with an ethyl group. However, when we count up our carbons and hydrogens and oxygens here, what we're actually going to find is that, and you know what, let me move this up. So what we'll find here is that this only adds up to, why is that black? So this only adds up to 134. So we're actually missing an oxygen somewhere. And we know that because oxygen weighs 16. And so our formula is going to be C9H10O2. So we need a second oxygen somewhere. And if we do an HDI on this formula, just to double check, just to make sure this is the right formula, it's going to be 2 times 9 plus 2 minus 10. So 20 minus 10 is 10 over 2 is 5. And so we have 5 degrees of unsaturation in the molecule that we've drawn. And the only place that we can really add an oxygen and keep these splitting patterns the way that they need to be and keep everything else the way that it needs to be is to put our aldehyde here again. But then this time to put an oxygen there as well. So an ether or a phenol rather. And so this, when we do this, this is going to add up to 150, which is what we need. And so this is the structure of molecule D. And again, we could have gotten here by starting at the mass spec, guessing at formulas, plugging things in until, we got to C9H10O2, and then doing the rest of the problem. But we have all the information that we need from the NMR. We pieced the molecule together and then noticed that it only adds up to 134. So we know we have to be short in oxygen. We plug that other oxygen in. The only place that it fits that will keep the splitting patterns of signals 1 and 2 how they need to be. And that's the answer to chapter 21, problem number 85.